Hi, in this lecture we are going to look at oxidation reaction as obtainable in organic chemistry. Now, it is very important that you actually study the oxidation reactions in organic chemistry because most reactions that occur in organic chemistry generally are either oxidative or reduction reactions. And it's also pertinent because we have various types of oxidizing agents and various types of reduction agent or reducing agent rather. Now, these oxidizing agents and reducing agents are prone to affect some functional group while oxidizing other functional group or reducing other functional group to get the desired product or the desired yield. Hence, it is necessary for you to understand the chemistry behind the oxidation of one compound to another so that you won't go and muddle up the whole process by choosing an oxidizing agent that may actually destroy a particular compound instead of giving you the desired yield. So, what is oxidation generally? Now we can say that oxidation can be defined in three ways. Now, one of the ways in which oxidation can be defined is 1. In terms of gain of oxygen. Now, whenever oxygen is added or oxygen is gained in an organic compound, you say that that compound has been oxidized. From the name oxidation, oxygen, are you getting it now? Has been what? Added. Now, the next one to define oxidation is in terms of removal of hydrogen. Now, whenever two molecules of hydrogens are removed, or let's say a molecule of hydrogen is removed from a compound, you say that molecule is being oxidized. Now, for every oxygen that is added in most organic reaction, now two molecules of hydrogen, or let's say one molecule of hydrogen, because when you talk about one molecule contains two atoms of hydrogen, right? Now, one molecule of hydrogen is being removed. Is that understood? Do you know why? Because oxygen is a divalent atom and hydrogen is monovalent. And because hydrogen is monovalent, if you remove one hydrogen, it will not be sufficient enough to actually balance the valency of oxygen that is added. So, two hydrogen atoms will actually balance the divalency of oxygen atom. Now, another term to define oxidation is in terms of electron removal. Now, when electrons are removed from a particular organic compound, you say that that compound is oxidized. That means you can say oxidation can also be looked at in form of increase in oxidation state. Increase in oxidation state in the positive direction. In the positive direction. Do you know why? Because whenever electrons are removed, what do you think will happen? In organic chemistry, if electrons are removed, what do you think is happening? There is what? The compound or the something becomes positively charged. The substance where the electrons are removed become positively charged. Right? Sorry. They become positively charged. So if you remove one electron, become one positive. Remove two electrons, become two positive. Remove three electrons, three positive. Remove four electrons, four positive, and then it continues like that. So these are the various ways in which oxidation can be defined. Now, the first one is that oxidation is defined as the addition of oxygen. So whenever oxygen is added, you say that that compound is being oxidized. Or you can also define it as the removal of hydrogen. That is, whenever hydrogen is removed, then you say that that compound has been oxidized. Or you can also say it's also removal of electron, or an electron is completely lost from a compound, right? Now, These are for oxidation. Now, how about reduction? Reduction is just the opposite of oxidation. Now, the focus of this lecture is for us to talk about oxidation and not reduction. So, talking about reduction is the opposite of everything we have here. So, reduction is when oxygen is removed, hydrogen is added, and electrons are added. In oxidation, electrons are removed. That means electrons are completely lost from a compound or a material or a substance in question. Is that okay? Now, let us look at some of the common oxidizing agents. What are some of the common oxidizing agents? Now, the most common oxidizing agent, as the name implies, is you have oxygen, which is O2. Now, other examples are HNO3, nitric acid. We have ozone. All these are oxidizing agents. Now, we have sort of inorganic compounds. Sorts of inorganic compound. All those are oxidizing agents. Examples of these sorts of inorganic compounds, that is where you have the most known organic oxidizing agent, which is KMNO4, potassium permanganate. Then we have ceramic salt. We have chromium trioxide, CO3. Now we have sodium iodate, lead tetraacetate, selenium dioxide, osmium tetraoxide. There are much. Osmium tetraoxide. Then we have nickel peroxide, etc. All these are oxidizing agents. Now we also have hydrogen peroxide and peracid. Hydrogen peroxide is a common oxidizing agent. You should take note of that. So these are the common oxidizing agents that we'll have. So if you are asked, give 5 examples of oxidizing agent, what would you say? KMNO4, potassium permanganate, ceramic salt, we have chromium trioxide, we have sodium iodate, lead tetraacetate, selenium dioxide, osmium tetraoxide, nickel peroxide, hydrogen peroxide, then peracid. We also have chromium, potassium chromate or heptazodichromate, right? K2CrO2O7. All these, they are oxidizing agents. Is that okay? All these are oxidizing agents. So you should be able to at least give 5 examples of oxidizing agents. Can we go together? 5 examples of oxidizing agent are KMNO4, the ceramic salt, the chromium trioxide, sodium iodate, lead tetraacetate, selenium dioxide, osmium tetraoxide, nickel peroxide, hydrogen peroxide, the peracid, and then potassium heptazodichromate. Now, all these oxidizing agents, they are useful for oxidizing varieties of organic compounds. And then there are some organic compounds that you may not really want to use any of these to just oxidize. You have to make a careful choice. You have to select which should be used for oxidizing a particular organic compound, so that you not mess up the whole process and mess up with the whole reactions. Now let us look at oxidation of functional groups, some functional groups that can be oxidized. Now we talked about the saturated hydrocarbons. Now what are saturated hydrocarbons? Saturated hydrocarbons are compounds that have only single bonds. And examples of these compounds are We have alkane. Alkanes are saturated hydrocarbons. They contain only carbon and hydrogen. And examples of these alkanes are methane, we have butane, we have pentane, and we have others. Are you getting it? Now, these saturated hydrocarbons, they do not undergo oxidation reactions. And because they do not undergo oxidation reactions, they are mostly not used in synthetic organic chemistry. That means they are mostly not used to synthesize other compounds. And that is why they are called paraffins. They don't easily react. Paraffins. Now, the reason is that if you oxidize saturated hydrocarbons, they will break. Saturated hydrocarbons break on oxidation. So you should take this. They will break on oxidation. Hence, they are not oxidized. Now, the next thing we are going to look at are aromatic hydrocarbons. Now, of course, when we talk about aromatic hydrocarbons, the first thing that should come to your mind is benzene. This is the structure of benzene. Aromatic compounds, right? Now, the question is, do these, like benzene, does benzene undergo oxidation reaction? Benzene on itself do not undergo oxidation reaction. But when benzene is substituted, the substituent can easily be oxidized. For instance, if you have something like this, let's say you have methylbenzene, which is commonly called toluene. Now, this methylbenzene can be oxidized by an oxidizing agent. If the oxidizing agent is mild, if it is a mild oxidizing agent, are you getting it? If it is not that concentrated and it is not that harsh, it will actually oxidize this to an aldehyde, which will give us something like this. This is an aldehyde. This is for mild oxidizing agents. There are some oxidizing agents that are very hot. Now, these are mild oxidizing agents. Now, how about if it is a very concentrated oxidizing agent? What do you think will be the product? The product will directly come to form a carboxylic acid. So you form something like this, OH. Are you getting it now? Which is called the benzoic acid. So that is that for aromatic hydrocarbons. Generally, they do not undergo oxidation reactions like benzene, naphthalene, atrazine. They do not undergo oxidation reaction. But however, if they are substituted, the substituent undergo oxidation reaction. But not all the substituents, which we are going to look at later. There are some certain conditions that must be met for these substituents to undergo this oxidation reaction. Now, the next thing we are going to look at are the alcohols. Now, alcohols are easily oxidized to aldehyde and then to carboxylic acid. So the chain of oxidation of alcohol is usually from the alcohols. Let's say primary alcohols are oxidized to aldehyde. And if the oxidizing agent is very harsh and concentrated, it will oxidize this aldehyde further to carboxylic acid. Now, while secondary alcohol are oxidized to ketone, and some vigorous reaction will proceed like that. Now, tertiary alcohol do not undergo oxidation reaction in a normal condition. They do not undergo oxidation reaction in a normal condition. But however, if there are certain things if the condition is vigorous, let's say a very harsh condition, they may undergo oxidation to form carboxylic acids. So in vigorous conditions, so under normal conditions, they do not undergo oxidation reaction. So like I said, under normal condition, tertiary alcohols, which are called a 3-degree alcohol, do not undergo oxidation reaction. But if the condition is a vigorous condition, they will undergo oxidation reaction to form what we call acids. So under vigorous condition, you can say here vigorous, they will undergo oxidation reaction to form acids, right? So that is that for general oxidation reaction. Now look at something. Can you actually picture what we said initially as oxidation, or as oxidation as the addition of oxygen or removal of hydrogen? Now if you look at this first one, you agree with me that this whole something was oxidized to give us the benzaldehyde. This is toluene, which is methylbenzene. There's no space to write it. This is methylbenzene. Let me just write it here. Now when it is oxidized with a mild oxidizing agent, it changes toluene to benzaldehyde. Now this benzaldehyde, if this methylbenzene undergo vigorous condition, like I said, vigorous condition, it must be under vigorous condition for it, or a very strong, when I say vigorous condition, I mean a very strong oxidizing agent, it will convert it to decarboxylic acid. So take note, we said that saturated hydrocarbons do not undergo oxidation reactions because they will break on oxidation. And those saturated hydrocarbons are compounds like methane, butane, pentane. Hence, in most organic reactions, they are not always used for organic synthesis, rather. That's why they call them paraffin. Paraffin means they lack affinity. When you say something lack affinity, it means that it does not react. Are you getting it now? When you say somebody lacked affinity, it means there's no emotional attachment to other people. They don't react. Now, so that is the general overview of oxidation and some of the compounds that can actually undergo oxidation reaction. If you look at this one here, in this particular place, see that one oxygen was added. And when one oxygen was added, how many hydrogens were removed? 2 hydrogens were removed. Look at it very well. There are 3 hydrogens here. But here, how many can you see? Just 1, and then an oxygen is added. Now, in this case, they actually added just oxygen without the removal of hydrogen. So you say this is being oxidized, and then even coming here, it was also what? Oxidized. Same thing applicable here. This one was also what? Oxidized. So that is that for oxidation reaction. Now let us look at some of the various oxidizing agents and the compounds that they will react with to form products. Now the first one we are going to look at is aromatic hydrocarbons. Now the aromatic hydrocarbons, we said they are compounds that have substituents on them like this. For instance, benzene is an aromatic hydrocarbon. But we say benzene will not ordinarily react unless a substituent is added. Now, when aromatic hydrocarbons react, the product that it usually forms is called a benzoic acid. So aromatic hydrocarbons usually react with KMnO4, which is potassium permanganate, as an oxidizing agent. This is potassium permanganate as an oxidizing agent, or permanganate, or it may use sodium heptazodichromate in H2SO4 at a very hot temperature. Are you getting it? Something very hot temperature, like let's say 50 degrees Celsius. It will give benzoic acid. Now the mechanism of this reaction is not something that is easier or very easy for us to understand now at this our level, because it's a free radical reaction. We are not to go into the mechanism of the reaction, but just know that whenever aromatic hydrocarbons that are substituted react, the product is usually benzoic acid. Now, another thing that you also need to know is there are some functional groups that are resistant to oxidation with KMnO4. There are some functional groups that are resistant to oxidation with KMnO4, right? So we can say KMNO4 resistant functional group. Now, what are those functional groups that are resistant to KMNO4? That is, if KMNO4 is present and this functional group are attached to an aromatic hydrocarbon, it wouldn't oxidize them. Now, these functional groups are, we have the sulfate functional group, which is this. This one is not easily oxidized by KMNO4. Another one again is the carboxylic acid functional group, not easily oxidized by KMNO4. Now, the next one that we are going to look at is NO2, the nitrate functional group, not easily oxidized by KMNO4. Is that okay? So all these functional groups here, they are not easily oxidized by KMNO4. So if you see all these functional groups attached to a benzene ring, and then you see KMNO4 also sodium heptazodichromate present in H2SO4, present in that situation, know that it will not oxidize it. Now, no matter the length of the hydrocarbon, the product is usually benzoic acid, because what reacts is this hydrogen. The place the reaction takes place is this hydrogen close to this carbon here. So the compound that must react must also possess a hydrogen close to the carbon attached to the ring. What I mean is, this is the ring here, right? Now, the adjacent carbon to the ring is this one. For this reaction to occur, this adjacent carbon must carry a hydrogen. If it does not carry a hydrogen, that reaction will not occur. And no matter how long the substituent is, it is at this carbon that is adjacent to the carbon in the ring that the reaction usually takes place. So when this occurs, this is what is going to form. It's going to form something like this. We have our double bonds, and then we have C. Here become double bond O, and here becomes, yes, C, double bond O, and here becomes H. So you call this benzoic acid. So whenever these aromatic hydrocarbons react, it usually form this benzoic acid. Now, same thing applicable here. If this one will react, what do you think is going to form? It's going to form this compound. Now, note the point of reaction. I told you that the point of reaction is usually the carbon adjacent to the carbon in the ring. So this is the carbon in the ring. This is the carbon adjacent here. Now, you have to look at it very well. Is this carbon having a free hydrogen? Because if it doesn't have a free hydrogen, the reaction will not occur. Now, if you look at this, this is one bond here, one bond here. This hydrogen, and then this is hydrogen. So you agree with me that there are two hydrogens here, because the valency of carbon is 4. And according to what I've been advocating ever since in organic chemistry, when you're giving compounds like this and then you didn't see any hydrogen attached here, just draw the bond, look at how many bonds are attached, and then add the number of hydrogen that will make it to complete the valency of 4. So this is where the reaction will take place in this particular compound, this or here. Hence, this part will leave. So the product of this reaction would be C, double bond O, and here is OH. And this is also benzoic acid. Now, in some textbook, you will see they will write it as this because it's only one substituent, so it doesn't really matter the position. You have it as this. Still the same thing with what we have there. Sorry about this. This is supposed to be OH, which is benzoic acid. So whenever KMNO4 or this chromium trioxide in H2SO4 reacts with compounds like this, the product is usually benzoic acid. Now let us look at another examples, practice question. Now you are given this. What do you think would be the product of this reaction? What do you think would be the product of this reaction? Now this is an ketone functional group. Now this is an alkene functional group. Now what do you think will be the product of this reaction? The first thing you need to look at is this resistance to KMNO4 oxidation? Come here. Look at the functional group I listed for you. These are the functional group that are resistant. So look at these ones. These ones, are they resistant? They are not resistant. So the product of this reaction would be something like this. No matter how long it is, it must always give you the benzoic acid at both sides. So this will give us this, and here will become C double bond O. Here is OH, right? And then here will still give us C double bond O, and here is OH. Do you know why? Because this is the carbon that is actually, and now at this carbon, this position, look at it very well. Is it having any hydrogen? And see if there's an exception to this. Now the question you may now want to ask yourself is this carbon here carrying a hydrogen? Now that is not, it's not carrying hydrogen. And when you come to compounds like ketones, aldehyde, etc., they can easily be oxidized. Now the reason why we said that this one must carry if you look at the point at which this one was oxidized, it was not oxidized here. Look at it very well. It was not oxidized here. Where was it oxidized? It was oxidized on this carbon. Do you know why? Because this carbon here is standing close to a carbon that is carrying a double bond. Look at it. This is the carbon here. This carbon is carrying a double bond. Then this carbon is the one adjacent to it. Now the reason why we said it must be adjacent to the double bond or to the ring is because in the ring there's always a double bond at this point, right? So any carbon that is adjacent to that double bond is susceptible to that oxidation. But in this case, you can see that this carbon here too is adjacent. When you say adjacent, very close to a carbon also carrying a double bond. Hence, this place is also susceptible to oxidation. So the oxidation will not occur here in the case of this compound, but rather it will occur here. Is that okay? So that is the reason why in this case the oxidation will occur here and not in this position. That is why we have it as OH here and not at this position. Is that okay? Now this one also will be oxidized because this one has the OH functional group here. I mean the hydrogen functional group here attached to this carbon. Hence, this will be the product of this reaction. Now, if you look at this compound very well, do you think oxidation will occur? Look at it very well. Now this is the carbon here, and then this is the adjacent carbon. Now this adjacent carbon, does it have any hydrogen? It does not have any hydrogen attached, apart from these ones here. And these ones here are not to be oxidized. Is that okay? Because they are not close to carbons carrying a double bond. This is the only carbon close to this carbon carrying the double bond here. Hence, the oxidation is supposed to occur here, but there's no hydrogen for that oxidation to occur. Hence, oxidation cannot occur here. Now, if you look at this one very well also, we added one oxygen and then we removed this entire group from here and then added OH. Is that okay? That is why we have this as the product of the reaction. Now, you may now want to say, why is it not like this? OH. If you do it like this, it will not give us the carboxylic acid we are looking for. Are you getting it? So it has to be like this. So compounds like this is ketone, can also be oxidized by KMnO4 to give us the acid derivative of it. So in this particular one, there will be no reaction. So you come here and say no reaction. No reaction here. All right. So that is that for the aromatic hydrocarbons and oxidation of organic compound. And I think that will be all for no. Let's try this one. Now, what do you think will be the product of these reactions? Now, this is chromium trioxide in H2SO4. If it reacts, what do you think is going to form? It's still going to form the product of oxidation, which is a carboxylic acid, right? It's going to form the product of oxidation, which is a carboxylic acid. So when this one reacts, it's going to form something like this. This is 4-methylpyrimidine. So let's name here. When it oxidizes, this will be oxidized also to this product. can be in any of the direction. And also this one too will also be oxidized. Now this point, there are 2 points in which the oxidation can take place, right? There are 2 points, which is this point and then this point. But before we even jump here, what is the name of this product? You can say the name of this product is pyrimidine 4-carboxylic acid. Now, why is it pyrimidine 4-carboxylic acid? We are taught when numbering pyrimidine that you start your numbering from here, then go to this one, here become 1, 2, here is 3, here is 4, right? You're supposed to be double bond, 4, 5, and then 6. So at position number 4, you have the carboxylic acid attached. That is why we call it pyrimidine 4-carboxylic acid. Now, how about this one? If this one should react, what is the name of this compound? It's like methyltoluene, right? Para-methyltoluene. Is that okay? Because there is methyl here and there is methyl here. This is benzene ring. Normally, methyl and benzene gives toluene. Then you now have another methyl here. That is para-methyltoluene, if you want to call it that way. But the nomenclature is not what we are after now. We want to look at the product of oxidation of this compound. Now, when this compound is oxidized, it's going to form an intermediate. How is the intermediate looking like? It's looking like this. Now recall that this 8C2O you are seeing here, it means acetyl group. This AC2O you are seeing here, it means what? Acetyl group. Now 2-acetyl group. How is the acetyl group like? It's like something like this. You have C, O, and then you have double bond CH3 and then O. That is how the acetyl group is. That is what it looks like. Are you getting it? This is what an acetyl group look like. It's more like carboxylic acid acetate, something like this. If I want to make it easier for you, this is the acetyl group. All right. So when this attaches here, what do you think will be the product of this reaction? It will be something like this. You have this, right? And then you have all the acetyl group attached to these positions. So this one come here, and then you have the double bond. Here is CH3, and then also this come here. Here is CH3, and here is double bond O. Now same thing is what to be applicable here. Almost the same. Double bond O, CH3, right? Let me drag it to this side. C, double bond O, CH3. You can draw it like this. You can draw it any of the way you feel is. You can actually spatially arrange them. You can take it this way. C, double bond O, CH3. That means the acetyl group attached. Now this is called the reaction intermediate. This is called what? The reaction intermediate. Now when this reaction intermediate is hydrated, that means you pass it through water hydrolysis, it's going to give 2 products. Now the 2 products, first of all, it's going to give 1 product. So let me erase this and then write the product here. It's going to give something like this. It's going to give a dialdehyde. Now we'll call this a dialdehyde. Now why do we call it a dialdehyde? Because this is an aldehyde functional group and this is another aldehyde functional group, right? So when this dialdehyde is oxidized, recall that this aldehyde functional group can be oxidized to give us an acid, and this can also be oxidized to give us another acid. So when they are oxidized, the product of this reaction will become a diacid, right? Dicarboxylic acid, which will now be something like this. Now we can decide to write it COOH, COOH, or if you have the time, you can decide to spread it apart. C double bond O, here's OH. If there's space, still the same thing. C double bond O, here is OH. So this is a dicarboxylic acid as our final product. So all these are synthetic rough or synthetic parts to actually get various types of organic compound. You see, we started with a methyl-toluene. From there, we reacted it with this chromium trioxide and H2SO4 with acetyl group here, which gave this reaction intermediate. So this reaction intermediate is from this group here. Are you getting it? This group attaches here, and then this one become, you hydrolyze it, call this hydrolysis. Now to give a dialdehyde. This dialdehyde react with this to form a dicarboxylic, or it is oxidized. The dialdehyde is oxidized to give us carboxylic acid. Recall that aldehyde can be oxidized to carboxylic acid. First of all, we said alcohols are oxidized to aldehyde. Look at it here. We said something about this, that first of all, primary alcohols are oxidized to aldehyde. Then aldehyde are oxidized to carboxylic acid. So that is that for these oxidizing agents we've looked at. So what are the oxidizing agents that we actually focused on in this lecture? The oxidizing agents are, we focused on KMNO4. We also focused on chromium or chromium trioxide and H2SO4. All these, they perform the same function, right? Or we focus on K2CR2O7 in H2SO4. When you see them like that, know that they will oxidize a methyl group attached to an aromatic compound to a carboxylic acid functional group. Is that understood? They will must always oxidize them to a carboxylic acid functional group. Now let us look at another example here. Now we have this one. This one is called chromine chloride. What's the name of this compound? Chromine chloride. Now, when chromine chloride is in tetrachloromethane, the product is, it will oxidize this to give us an aldehyde. The reason is because chromine chloride, the tetrachloromethane, is a mild oxidizing agent. So you can take it, this is a mild oxidizing agent. Now we said mild oxidizing agents do not oxidize compounds to give us carboxylic acid. They will rather end at the aldehyde functional group. The chain usually goes from alcohols to aldehyde, from aldehyde to carboxylic acid. So when you use a weak or a mild oxidizing agent, it's expected that you stop at what? The aldehyde functional group. So when chromine chloride reacts with this, the product, instead of us getting a carboxylic acid, you are going to get something like this. CHO and then Br. Now when this is further oxidized, it's going to give us the desired product. Is that okay? Now in the same vein, hydroquinone. I know most of us we must have heard of hydroquinone before. There's this bleaching cream that they usually sell. I'm forgetting the name of that bleaching cream. Said they contain hydroquinone. Most of these bleaching cream you see, they contain hydroquinone. So when you have an understanding of all this, when you see a cream that usually contains this hydroquinone, you know that it is not good for your skin. This extract, does extract contain hydroquinone? I know there is one. What's the name of this popular bleaching cream? Contains hydroquinone. This CrO3, the same thing with acetic acid. All these on the oxidizing agent. Now when these react, the product is it will form benzoquinone, right? We form benzoquinone. Benzoquinone is something like this. Double bond O, double bond O. Reason being that this functional group here is oxidized to aldehyde, from aldehyde to what? Carboxylic acid. This is a strong oxidizing agent. So it didn't pass through all those steps, just straight to, it oxidizes it to a ketone. It oxidizes it to a ketone, not to a carboxylic acid. Sorry, this is a ketone. And the reason why it is like that is because this hydroquinone, let me write this here. Hydroquinone is a secondary alcohol. Alright, it's a secondary alcohol. And from the relationship, we said primary alcohols 1 degree will always go to aldehyde. And then from aldehyde, if they are further oxidized, they will go to acids. While secondary alcohols are always oxidized to ketones, and then they will end there. Right? So this hydroquinone is a secondary alcohol which is oxidized to benzoquinone. There's this bleaching cream I'm trying to remember. Miss Carol White. Miss Caroline. Now Miss Caroline contains this hydroquinone. Most of this bleaching cream also, they contain this hydroquinone, and they are good bleaching agents. Most oxidizing agents are bleaching agents. Are you getting it now? So you should know all that. Now, the oxidizing agent, there are some of them that when you actually put them in some compounds, some of these compounds are sensitive to them. And because they are sensitive to them, they tend to destroy the entire compound and then muddle up the whole processes. Now, there are some of these oxidizing agents that are acids, that are sensitive to acid functional group. Or we can say that they are acid sensitive compounds. Now, acid sensitive means those compounds that have one double bond. In terms of alkenes, they are acid sensitive. Do you know why? Because this double bond is capable of donating a lone pair of electrons. What did we define Lewis acid as? We said Lewis acid an electron acceptor. So anything that has a double bond is capable of donating electron to it, right? Now, compounds that have lone pairs of electrons are also acid sensitive. Are you getting it now? Alkyne also, they are acid sensitive. Alkyl bond, which is triple bond, they are acid sensitive. Now, what other acid sensitive compound do we have? OH of alcohol. Do you know why? Because this OH of alcohol, they are bases. And you know base and acids will always react. So you call them acid sensitive compounds. Is that okay? So there is need for us to actually select some of these oxidizing agents that will not affect this functional group. And examples of such oxidizing agents are, we have manganese dioxide, silver oxide. Let me clean all this. So like I was saying, if you have, let's say, an olefin or a double bond in a particular compound, you know that this double bond is acid sensitive. Are you getting it now? If you want to use an oxidizing agent to react, you must make sure that that oxidizing agent will not oxidize that double bond, especially when you don't want to oxidize the double bond. And some of those oxidizing agents that can be used in that regard are, you have manganese dioxide. Now you have silver oxide. Now another one again is I think these ones, they are okay, right? you can reduce them to actually react without affecting the double bond or without affecting the olefins double bond. Now when you say olefins, you're talking about alkene double bond, right? Also, these ones, they are used for oxidizing primary alcohols only, primary and secondary alcohol. It means that you can conveniently use this to actually oxidize primary and secondary alcohols without affecting their double bonds, right? Now, what I mean by that statement is, for instance, let's say this is CH3 double bond, let's say CCH2 double bond, CH2OH. Now you can oxidize this. If you oxidize this, what do you think will be the product? To give us, using the oxidizing agent silver oxide, it will give CH2 double bond CHO without affecting this double bond here. Are you getting now? Without affecting the double bond. That's why we said that there are some of them that are sensitive to particular functional group. So if you want to actually react compounds, if you want to oxidize alcohols that has double bond and you don't want to affect the double bond, use this one. Is that okay? Now, also, you can use chromium trioxide in pyridine for the conversion of alcohol that contain acid-sensitive functional group. Still the same thing. Now, recall that chromium trioxide we've been looking at since. We've used chromium trioxide to actually carry out some oxidation reaction, like chromium trioxide in H2SO4. This is highly acidic. The way it is, chromium trioxide in H2SO4 is highly acidic. Are you getting it now? So it will affect the acid sensitive functional group. Do you know why? Because it will make this one to be very, very much acidic, and because more acidic, it will affect this double bond here. Is that okay? More like, the more this is acidic, the more this we want to react, because these double bonds are bases, they are nucleophile. Can we still remember all that? Yeah. Same thing is applicable to what I'm saying here. Now, in this case of chromium trioxide in pyridine, it's something like this. Let's take this one for instance. Chromium trioxide in pyridine. Now, pyridine is a base. Pyridine is a what? It's a base. Now, because pyridine is a base, it will make this chromium trioxide to be basic. And this double bond here is what? Basic, which is this alkene double bond. So you can actually react, because this is base, this is base. What it concern us? Are you getting it now? There's no normally acid and base will react, but base and base, they will just be there. Is that understood? So the reason why we use pyridine is to make this oxidizing agent to be basic in order not to affect this double bond here. But actually, it will oxidize this group here. So in this case, this group OH here is being oxidized to give us the product, which is something like this. So this one will be oxidized to give us oxygen here. I decided not to put it because I know I'm going to put it here. So this is being oxidized to this. Is that okay? So that is basically the use of oxidizing agents, some that are acid sensitive and others that are not what? Acid sensitive. So if you are given a choice of compound, like let us say you are given an exam, then they give you, say which of the following can be used to oxidize this without affecting the double bond. You know that you can use chromium trioxide. Take note. You can use chromium trioxide in pyridine. Now you may be asked, what is the usefulness of pyridine in this reaction? Because pyridine makes this oxidizing agent to be what? More basic. Hence, it will not affect this double bond here. All right. Now, what do you think may happen if this is an acidic compound that is added here? Let's say something that is acidic. Instead of pyridine, they use H2SO4. Conc H2SO4. It will make this to be very acidic, and then it will affect this double bond here. And this double bond now may now want to be oxidized to give either a glycol or another kind of organic compound. Now, we have what is called the Openia oxidation reaction. Now, we are giving this in an exam. They said, what is the name of this reaction? Now, you can say the name of this reaction is 1. The name. The name is, I've stated it there, is also there, the Openia oxidation reaction. Don't go and write reaction like this, so please write it in full. Now, what are the oxidizing agents that are used in the Openia oxidation reaction? The oxidizing agents that are used are, you have aluminium alkoxide, right? Let's say aluminium butoxide in this case. Or proposide. Can we use butoxide? Aluminium butoxide. Right? In acetone. Now, what does this reaction entail? It entails the oxidation of an alcohol group here. Now, what kind of alcohol group here? Secondary alcohol to a ketone functional group. So secondary alcohols are always oxidized to ketones. Those are the things that we need to understand. Secondary alcohols are always oxidized to ketones. So this is oxidized to this with there is what we call a bond shift to form an alpha beta unsaturated ketone. Now, what do we mean by that statement? You discover that there was a bond here, but in the product now the bond is not here, right? That means there is a shift of bond from here to this position. Now, this position is what we call the alpha position. This position is what we call the what? Beta position. Reason because this is the position kind of functional group. We said the group close to that position is called the alpha position, while this is called the beta position. So we call this an alpha beta unsaturated. Unsaturated is because there's a double bond between the alpha and the beta carbon. Ketone, because normally this is ketone. So the Openia oxidation is an oxidation reagent that is used, or is a pharmaceutical, or let's say it is used to convert secondary alcohols to alpha beta unsaturated ketones. Or you can say it is used to convert an unsaturated secondary alcohol to an alpha beta unsaturated ketone. That is the usefulness, the pharmaceutical usefulness of it. Are you getting it now? Usefulness of the Openia oxidation. So take note of that. I know there is a particular question that came out in one of the exams. Now, like I said, this reagent here is not restricted to only this. You can also have it as AlOCH2 3, right? It's very easy. Oh no. We cannot actually use this notation for it. Let's just make it easier by doing it the way it is. This is OC3H7. It's better like this. Now the reason why this 3 has to be outside is because aluminium has an oxidation state of +3, while this one is minus. So this gives us C is an alkoxide, CH3O7. When they exchange valency, this 3 will come here and this one will come here. That is why this compound is like this, right? So that is that for the Openia oxidation. Oxidation with a shift of a double bond to form an alpha beta unsaturated ketone using aluminum alkoxide as the oxidizing agent in acetone. This is aluminum hydroxide in acetone. Now the next one that we are going to look at is lead tetraacetate. Now lead tetraacetate in boiling benzene, it can either be in boiling benzene, you can also use it in hexane, you can also use it in chloroform. Now, when you use it, it is a good reagent in converting primary and secondary alcohols to carbonyl compound to give very good yield. It can give up to 80%, 90%, 85% yield. Are you getting it now? Now, it could also be in pyridine. So we have lead tetraacetate. Now, first of all, what is tetraacetate? We have to know what acetate is. Acetate is something like this. C, double bond O. This is acetate, right? Which we can decide to write as, this is O, C, then we have O, CH3. The reason why it is acetate is because this is acetic acid. Remove the hydrogen, becomes what? Acetate. So we have it as OCH3. Now, lead usually have the most stable oxidation state as either +4 or +2, right? So the reason why it is called lead tetraacetate is because there are 4 acetates bonded to lead. So you can write it like this, lead tetraacetate. Now these reagents are very important because I believe in this part of this exam, what they'll be asking in the reaction condition, the reagent that is used to convert this to this, right? So it converts it to carbonyl compound, which are either aldehyde or ketone, not to carboxylic acid. So we can say that this is a mild oxidizing agent. Lead tetraacetate in this O. It can be in pyridine, can be in any one of these one, but let's leave it in pyridine according to what is in the material. So when this is oxidized, it's going to give CH3, CH2, CH2. Here will be CH. These are many 1, 2, 3, 4. CHO. Right? Now, what is the name of this alcohol? You don't need to know. Just know that this is a primary alcohol. Oxidized to what? An aldehyde. So we can say that this is an alcohol. What kind of alcohol? Primary alcohol. Or you can say 1 degree alcohol. And then this is an aldehyde. Now, the same lead tetraacetate can convert in pyridine. It can actually oxidize this. Now, this is an alcohol functional group 2. Secondary, this primary, secondary alcohol. This secondary alcohol. If we oxidize these 2 secondary alcohols to ketone, so the product of this reaction would be something like this. You have this, you have this, you have this. Here will become double bond O, CH3. Here become double bond O, and here becomes CH3. And that is the product of this reaction. No. This is supposed to come down first, then go up. And this is the product of this reaction. Now, this is a ketone, a diketone. Now, do you know why I call it diketone? Because there are 2 ketone functional group here. So it's very, very easy. Now, same thing applicable here. Now, you see that this lead tetraacetate too, inpyridine, is a mild reducing agent. So it did not actually affect this double bond. Why? The double bond is acid prone. So the need for us to use pyridine, which is a base, to actually avoid the further oxidation of this to any other group, because this one is prone to oxidation too with a very or highly acidic reagent. So this will also give the product where only this group here will be oxidized. Now this is a primary alcohol, so we say secondary alcohol here, or 2 degree. This is primary alcohol, 1 degree. So the product will be pH, CH will still be there, CH, CHO. Now this is an aldehyde. Is that okay? So that is basically all for the oxidation of organic compounds, especially the ones that are aromatic and the ones that are acid sensitive. So we've looked at all those in this lecture. Now, what were some of the oxidizing agents that we used in this lecture? Can we still go back again as a way of revision? What are some of the oxidizing agents? We talked about lead tetraacetate. We talked about aluminum alkoxide in acetone. We talked about chromium trioxide in pyridine for acid sensitive functional group. Then we talked about chromium chloride. It's a mild oxidizing agent that changes the alkyl group to aldehyde as opposed to strong oxidizing agent which will oxidize them to carboxylic acid direct. Then we also talked about chromium chloride in ethanol, right? Chromium chloride in ethanol, which ethanoic acid rather, in ethanoic acid. Ethanoic acid is a weak acid. So it oxidizes the secondary alcohols to alkanes, to ketones, which we call this benzoquinone. Take note of that, right? And we also talked about magnesium dioxide and silver oxide. All these ones, we said they can be used to oxidize primary and secondary alcohols to carbonyl compounds without affecting the olefin double bond, right? Then we talked about how the CH3 group can be oxidized directly to carboxylic acid by using strong oxidizing agents like chromium trioxide in acidic medium. This is very strong. Then also chromium dioxide in acidic medium in this, you also oxidize it to that. Same thing applicable here. Now we said in this case there will be no reaction because there is no hydrogen that is attached to this carbon here is not attached to any compound carrying double or to any group carrying double bond. So there will be no oxidation here. So I believe that is basically all for that. So if you are given any reaction like this one now, say what is the product of the reaction, you know that this group will be oxidized to carboxylic acid. This group is also oxidized to carboxylic acid, and it continues like that. So that is all for this lecture. Thank you very much for your time. And examples of course, oxidizing agent: Chemendo for ceric salt, sodium iodate, magnesium oxide, silver oxide, nickel peroxide, osmium tetraoxide, peracid, hydrogen peroxide, lead tetraacetate, and then we have other selenium oxide. We named a few of them in this lecture.